Okay, so now let's take a look at the spectral classification for stars, and you will need to memorize the letters that are chosen for the classification, and also, most importantly, the order. And we'll go over that in just a moment. But the spectral classification is ultimately based on two things. Number one is the composition of the star, and by composition I mean of the atmosphere. And then number two, and this would be probably the most important aspect, is the temperature. And of course we're talking about the surface temperature. Now the surface temperature, of course, will be strongly related to the color, as we just saw in the previous topic. Stars that were very cool looked more towards the red. Stars that were warmer or in the middle of the temperature range are more in the yellowish or greenish portion of the spectrum, and those that are very hot have temperatures that puts them so that they release a lot more of the blue than the red, and so they appear kind of bluish. So the spectral classes were developed by a woman named Henrietta Leavitt at the Harvard observatories in the early 1900s, and this was her primary job, was to look at spectra. Essentially, they take pictures of star fields, but instead of seeing stars, what you would see is little spectra like this. And she would look at them with a magnifying glass, or with a microscope, I should say, and look for the lines and look for those things that reveal the surface temperature and the composition, and then began to group them together, and this is the system that she chose. So it's a little unusual the way that the letters go. They don't go in alphabetical order. But the 7 spectral classes are O, B, A, F, G, K, and M, and our star is a G. Within these classifications, then they break them down 1 through 10. So O10 being the top, and M1 being the lowest, the smallest, coolest star that you can possibly have. And our sun is a G2 star. So we're down here kind of in the lower end of the temperature range. To remember the order for the stars, the thing that I was given, or I have always been told, is O, be a fine, either girl or guy, kiss me. You can make your own mnemonic. It's really up to you to decide how you want to try to remember this, but one way or the other, you need to be able to put these stars in order, particularly knowing, for example, if they had asked you to compare a B to a G-type star, the most obvious thing that you would compare these two stars is their surface temperature, and you should be able to say that a B-type star is hotter than a G-type star, and you should be able to say something about their color. The O's and the B's will be more of a blue or a blue-white. As you get down to the A and F, A is going to be like a white-type star, or even slightly still bluish. F is going to be like a white star. G will be a yellowish colored star. K is going to be kind of orange, and then M is going to be sort of a reddish color. And you can see this in the graph, and you certainly don't need to copy this graph. They have a similar table for you in your textbook. But the hottest stars, this is giving the middle of the range. So the middle range for the O-type stars is about 41,000 K. For B, it's about 31,000. Then we drop dramatically down for the A stars to just under 10,000. The F stars, 7240. The G-type stars, you can see our sun at 5,800 degrees. If you remember, we just calculated that. So 5920 being a characteristic temperature for a G-type star, that's closest for our sun. And then for the K-type stars, 5,300, and for the M-type stars, 3,850 would be an average temperature, the lowest temperature for a star being slightly over 3,000 degrees. In other words, the smallest stars, the smallest objects in the universe that actually have that nuclear reaction going at their core, will produce a temperature a little over 3,000 degrees and then maintain that temperature for a long time. Now, one of the things about these stars that I do want to make clear, though, is that because of the temperature of the star, certain atoms may not give off light or may not absorb light. So let me explain what I mean. If you notice, they actually specify in this table prominent absorption lines. So in the O-type stars, you would see the helium. You would see oxygen, double ionized oxygen, double ionized nitrogen, double ionized silicon, helium, hydrogen. So as we move down here, you don't see some of the double ionized atoms. The A-type star is the one that produces the strongest hydrogen lines, hydrogen being the main ingredient in every star in our solar system, in our galaxy, I should say. Calcium and magnesium single ionized start showing up for the first time. In the F-type stars, the H line starts getting weaker. But we still see the ionized calcium, and then we see other metals like iron and magnesium and nickel. In our sun, the hydrogen lines, even though the sun is mostly made up of hydrogen, those hydrogen lines are a little bit on the weak side. The ionized calcium is a little bit stronger than the neutral metals. The only star that actually would show molecules, that actually is at such a low temperature that molecules can actually withstand that temperature, are the M-type stars, and that's titanium oxide. And that's what sapphires and rubies are made out of. So those stars actually have molecules in their atmosphere. Above about 4,000 degrees, no molecules can withstand that. All molecules will be broken apart, no matter what it is. Diamond, water, anything. It will be broken down to its individual atoms. Now, why do certain lines show up in some stars but not in others? Well, there's two things that could happen. Number one, if you heat an atom up too much, all of its electrons leave. Now, if all of the electrons leave, there are no electrons to absorb the photons of light. So without any electrons to absorb those photons of light, that light will pass through without being absorbed like it would normally be if you had the same atoms but it was at a lower temperature. And so this is characteristic as you get up into the very hot stars. You start seeing that as the stars are getting very hot, they are completely removing all of the electrons. So for example, for hydrogen, the reason why hydrogen does not show up very strongly is because the hydrogen can barely hold on to any electrons. Without the electrons, it can't absorb the photons of light passing through. That's one issue. That's if you're too hot. Now what happens if you're too cold? Well, if you're too cold, or I should say the temperature of the star is too cold, you may not ionize you not be able to make the jump high enough for it to occur. So I'm going to give you an example. The first jump in hydrogen, if you jump the electron up to that first level, second level I should say, and then let it fall back down, it produces an ultraviolet form of light. So therefore, if you're not making it jump high enough to at least get to the third level, I'm sorry, I don't know why I keep saying that. So first, second, third, fourth level. If you don't make it jump at least to the third level, it cannot release visible light. Now, how will it release visible light? Because on the way back down, it'll make two jumps. So instead of making the one jump, which we already know only produces ultraviolet light, it'll make this in a series of jumps. And so in this case, I can get visible light coming out. Now if I jump up to the fourth level, then these transitions from 4 to 2 and from 3 to 2, those correspond to visible light. So if the star is hot enough to make the electrons jump all the way up to the third or fourth level, then those photons of light can be absorbed, and we'll see the spectral lines. But if it's only making it jump up to the first level, then we're not going to see them. And the hydrogen lines, as you get down here, are extremely weak. In fact, in the M-type stars, they hardly show up at all. And just to give you a sense of this, let me show you the actual spectra of the 7 types, the 7 spectral classes. So here are the spectral classes. So we have 2 representatives of almost all of the stars. So I have an O. Then I have 2 different B-type stars, 2 A's, 2 F's, 2 G's, 2 K's, and 2 M's. And what you'll notice is that certain of them show spectral lines, and then the lines disappear. So let me find, so this is actually one of the hydrogen lines. As we said, in the A-type star, this is where that line is the strongest. But you notice as I move up, it's getting weaker to the point where it's almost gone. And as I move down, by the time I get to about the G-type star, this hydrogen line is all but disappeared. And you see the same sort of thing over here. The lines are strong here in the A, but above the A and below the A, we really see almost nothing. As I said, titanium oxide can actually hold itself together in the M-type stars. So here's 2 M-type stars down here at the bottom, and here are some of those titanium lines. But you notice by the time you get to the K-type stars, they're not showing up anymore. Now in this case, it's because the titanium oxide is being broken apart into titanium and oxygen by itself. And so of course the titanium oxide can't produce its characteristic spectral lines. What also shows up well in cool stars, well, the sodium lines show up pretty well in the cool stars. But as you get up to our sun, which we're right about here, in between G0 and G5, those sodium lines are a little bit weaker. Let me see what would be another one here. So unfortunately, the spectra don't show the lines quite as clearly as I would like. But what you can see is that certain spectral lines, and they're labeling the spectral lines on here, show up well in one star but not in another. Well, this is the way that we classify things. So, for example, as you saw in the chart, we would see certain atoms that show certain spectral lines, they become an A or an F or a G, and it's consistent with their surface temperature. Very consistent with their surface temperature. And to just sort of make this a little more concrete, here is a table that shows the line strength, so how dark and how wide those lines will appear at different temperatures. So for example, our sun is at about 5,800 degrees. So that puts us right about here for the sun. So as we go up through here, what would I expect to see? Well, I would see weak hydrogen lines. You notice the hydrogen peak is way over here, down here around 10,000. I'd see pretty strong iron lines, and I would see reasonably strong calcium lines. Not as strong as, for example, a K star or an M star. You can see that for a K or an M, the K-type star, the calcium lines show up great. Now what about the really hot stars? Well, similarly, the really hot stars also do not show the hydrogen lines very well. So let's say, for example, at 25,000 degrees, Well, at this point, the hydrogen lines aren't really showing up any better than they are for our sun, which is at a temperature only about 1/5 of that temperature, but for different reasons. Our sun doesn't excite the hydrogen enough to produce visible light. This star is actually exciting it so much that the electrons are actually leaving and no longer able to absorb, or rarely able to absorb those lines. So what shows up very strongly in the very hot stars? Well, the helium. Either helium or ionized helium. Singly ionized, meaning that it's lost one electron. These are things that would show up very strong in the hot stars. And then as we get to around the A-type stars, this is where you're going to see those hydrogen lines very strong. That's like just the right amount of temperature. Not enough to make the electrons go away permanently, but enough to make them jump past the second level to at least the third, fourth, fifth level. So you're going to see lots of visible spectral lines for hydrogen at that temperature. So it's a little bit of a, this is a really incredible complication that the spectra produce, and that is that the atom may be present in the star but not show up in the spectra, so it really kind of complicates things and makes it challenging to figure out what the stars are actually made of. But we know about which stars show up, and you can see the spectral classes running along the top up here. Right? So the M-type stars, the titanium oxide just makes it for the M-type stars.